The recording is live. My mic is working. All right. Before we jump into today's topic, which is the start of module exam 2, I just kind of wanted to briefly talk about the exam as performance. Sadia, right? Yeah. Talk a little bit about the exam and just some things that I noticed regarding performance that will help us understand how to approach future exams and a little bit more about how I grade. Number one, on your exam copy, the only things I've marked is if something was wrong. So if you see if you have an answer that there's no marking, that means that's a correct answer. Elliot. Yeah. Okay. Sorry about that. Okay. Just wanted to talk a little bit about some of the problems that I saw. First off, the true and false section. Um, Pretty straightforward performance. I'd probably say the average for this was a 7 out of 10. For the most part, the big issues came in the latter half. Just kind of wanted to talk a little bit about each of them. A bond order of 0 represents an unstable molecule. The noble gas configuration for copper, some students put a false for that one. Of course, it was on, what's your name? First, wait. Noble gas configuration is one that expected you to recognize that, of course, there was a 2+, so you needed to remove 2 electrons. Electron affinity, this was one of those periodic trends that we talked about in class. I talked about how from left to right, it actually gets smaller. So it does not increase from left to right. Number 8, the molecular formula for ammonium sulfate. Ammonium is NH4 plus, sulfate is SO4 2 minus. So upon crisscross, there should have been a bracket around the NH4 too. In 1.56 times 10 to the 4, there are actually 3 significant figures. Exponents are not included in our discussion. And for the last part, I think maybe that's the first part of the phrase really threw people off, the all diatomic molecules. Ultimately, to be paramagnetic, you simply need to have unpaired electrons. The multiple choice was also a standard performance, just talking broadly. Which ion has the largest ionic radius? If you recall, ionic radius does not have a trend. It instead depends on if it's positive or negative. What I had told you was the more positive, the smaller. So if we're asking for the largest ionic radius, we're looking for the least positive of the bunch, +1, +2, and +4. +1, of course, is the largest one. Noble gas notation, a lot of people had incorrectly put A as an apple. Maybe you just didn't realize that you needed to remove the 2 electrons based off the 2+. For iron 3 phosphate, some students incorrectly thought that the 3 just referred to the amount of ions present, not specifically the charge. If you did recognize the charge, you'd get 3+ and 3-, 1-to-1 ratio. Now, number 5, something I did notice during the exam for number 5 was people were starting to draw those MO diagrams for oxygen to answer this question. You did not need to do that level of detail. You could have remembered that bond order is directly related to the number of bonds present. And oxygen was one of those atoms that we went through that discovered that it has a double bond. All right. So that is, of course, why the bond order is 2. You did not need to draw the MO diagram to figure it out. You could have identified that. Scientific notation was good. Element as electron affinity is good. Number 9, the molecular orbital diagram of N2 shows, again, you did not need to draw the MO diagram. If you had remembered that nitrogen has a triple bond in between the 2 atoms, you could have identified that it has a bond order of 3. In the copper sulfate, the charge of the transition metal, a lot of people did correctly identify that the copper would be positive, but some people put +1. Remember, of course, that sulfate is 2-, and if these 2 are in a 1-to-1 ratio, that means copper must be 2+. Across the board, the nomenclature section was in my opinion, I think it was one of the worst performing sections. I think this ultimately comes back to just memorizing and understanding when, how do I put this? Understanding the rules. So for example, here, barium carbonate, some students had incorrectly written barium carbon oxide, meaning they had not recognized or remembered that CO3 is a polyatomic ion. And of course, that would be incorrect. In the case of the dinitrogen pentoxide, even though we had gone over this in class, that the Greek prefixes refer to the number of each atom. So dinitrogen is N2, pent is 5. Some students had it mixed up. They had N5O2. Some other small issues here was just not remembering or recognizing the Roman numerals as the charge. Some people for zinc chloride put Zn2Cl, which is of course incorrect. Some other issues that happened here was, again, a misremembering of what the polyatomic ion is. This is Cn as in cyanide. Some people wrote carbon nitride, which is of course incorrect. For this one right here, this was just a sulfate ion. Some people incorrectly wrote sulfide. I'll have you remember that ide is only used when it's a regular element that's dropped its suffix. So sulfide would just be the regular S. Here, I'm not sure exactly what happened. I had a lot of responses that labeled Ag as gold. I'm not entirely sure where that came from. I'm assuming just where they were on the periodic table, just people misread it. But this is just one example of what I mean by I've given you the periodic table, but it's on you to be able to read and identify the information correctly. S2 minus, this was another one where students had incorrectly thought this was a polyatomic. They had either written sulfates or sulfites. But of course, the correct answer is sulfide. Permanganate was okay. Here, we had some covalent compounds, the dinitrogen touch oxide, the dihydrogen monoxide, and the sulfate. Across the board, like I said, the biggest issues were misremembering or confusing the rules. There were a lot of cases where even though we do have transition metals like the silver here, some people forgot to include the Roman numerals. Now, problem 4, fill in the blank. This was a new type of question for me. I purposefully did not give you a word bank, a phrase bank for you to pick from, because I wanted to see what the variety of answers would look like. You can see for number 1, I said the atomic number of a neutral atom is always equal to, if you had written either number of protons or number of electrons, you got it correct. The quantum number that describes the shape of an orbital, its name is azimuthal, but if you had written the symbol L, you would have also gotten it correctly. Number 3 is actually a really good example of what a problem I noticed, which was a failure to read the question correctly. Number 3 explicitly says a molecular orbital formed by the destructive overlap is called and I think some people had their answer constructive. Some people also wrote the answer destructive, even though it was in the sentence itself. So I think the biggest issue with the fill in the blank was just reading the question too quickly or just not reading it correctly at all. Here, significant figures, this was a good performing question. 1, 2, 3, 4, 5. We don't include the exponents. The charge of the potassium ion. Okay, so for this one, I kind of bear some responsibility for not making the question clearer. A lot of people for a charge simply just wrote positive. I, of course, was looking for +1. So if you simply wrote positive, then you would have gotten half credit. The electron configuration for a neutral chromium atom is 4s1 3d5. Some people did not recognize that I gave them the noble gas and had written out from the 1s1, 2s2, all that way. That would have gotten half credit. I would just want to highlight this one right now, the neutral chromium atom. Number 8, one of the most commonly known diatomic elements. So you could have written any one of the bunch I talked about in class. If you had even just written the word H, I would have accepted that as well. Of course, it did not need to be too specific. Number 9 was very good. Everyone got the difference between what a neutron is, how to calculate it. And number 10 had the same issue as number 6. I asked you to tell me, the charge of the cation. Some people just wrote, again, the word positive. That's an insufficient answer. You needed to specifically tell me that it was +1. The periodic table, this was one of the highest performing questions. This was one of the problems we went through in our in-class problem set. I did give you the hint that this would be on the exam. One immediate issue I noticed from people was you did not round to the nearest whole number. I did have in the instructions, do not use decimals in your answer. And as a result, if you did use decimals, you either would have gotten a half point taken off or more if it kept occurring. The other issue I saw here was talking about the charge and how it relates to number of electrons. Remember that I've defined for you the charge in some cases, so the number of electrons must reflect it. In a neutral molecule, the atomic number is equal to the number of protons and the number of electrons. But in this case, this is 2 plus. So you needed to remove 2 electrons, meaning 26 in total. Same thing right here. I told you the atomic number. I told you the number of electrons. It's on you to recognize that they're not the same. So the charge is not neutral. Neutral, of course, be incorrect. The other issue I saw was an improper rounding. Now, mercury, according to the periodic table, is 200.59. This one rounded is 201. If you had written 200, I would have given you half credit, or I would have taken off a full point, again, if it occurred multiple times. But these were just very small mistakes. I think the average for this question was 13 out of 15. Very good performing section. The worked problems. Okay, I want to actually show you something about this particular question. We have here a full equation written right here. Now, oops. I'm going to actually put it on my calculator to show you what the answer should be. I don't have the immediate thing. I'm just going to look at Joel's screen, one right here. 3.405 times 10 raised to the 4 multiplied by 2. Whoops, that looks a bit ugly. Times 2.01 times 10 raised to the negative 2 bracket, all over 6.0 times 10 raised to the 3. You put that into your calculator as is, you should get the answer 0.114, which I've written right here. I did a little different. I did it step by step, which when rounded to 3 significant figures. How do we know 3? This is 4. This is 2. I'm sorry, that's 2 significant figures. This is 2. So when rounded, we go 1, 2. After the second decimal place tells us we should round up. Depending on how you put it in your calculator, some people got times 10 to the negative 5. This is a good example of what I talked about in the beginning of the semester, where your calculator could be your best friend and your worst enemy, where if you don't know how to use a calculator correctly, you will get an incorrect answer. If you did have something along the lines of this 1, 2, or 1.2 times 10 to the negative 1, you got credit for it. For part B, I thought I was being a little clever. Part B said to draw an orbital below for a neutral chromium atom. You actually would have answered this in the fill in the blanks. I did recognize that some students had correctly gotten number 7, did not correctly get the diagram. So that tells me that there's a little bit of disconnect in trying to understand what you're supposed to do. If you had gotten it correctly in the fill in the blank, you would have remembered that this was 4s1 3d5, which means that some people, they put 2 of them in 4s and they only had 4 in the 3D. That's, of course, incorrect. Part C, I would probably say, was unsurprisingly one of the worst performing questions. I say unsurprisingly because if you remember, that was the day we had a power outage. So that lecture could not be recorded. So I walked into this exam thinking, I'll only give them one MO diagram question just to kind of test. But what I saw was a small misunderstanding. So notice that in all of these cases, I had told you with a charge, F2, 2 plus. That 2 plus tells us that we should lose 2 electrons. Some people removed 2 electrons from each fluorine, meaning that technically you should be 4 plus based off of that logic, right? That's incorrect. Some people did not recognize that there was a 2 plus and filled in all the way. And there were some students where I would think that maybe there's a fundamental misunderstanding because even though they had correctly written the fluorines, they had just filled up the MO diagram the full way. And that's, of course, incorrect. This was a kind of question where your mistakes did carry over. If you got partial credit for your MO diagram, but your bond order was correct based off your incorrect diagram, you would have gotten 1 out of 3 points, right? And for the paramagnetic or diamagnetic, it was an either or. So either you got it fully right or fully wrong. This is all to say, I understand that the MO diagram was probably the hardest topic for you to study for, prepare for on the exam. Don't worry too much about it, as we won't really see it again until the final. It's very isolated where we cover it. But above all else, I would say that this exam, the average was a 62. That's about what I would expect for the first exam of a general chemistry class. Your extra credit, you should see the total score on Canvas, meaning on your exam, you should see the raw score without extra credit. And then on Canvas, I've added your extra credit to it. Some of you submitted your extra credit late, which means there is a late penalty. So you may not have gotten a perfect 5, but you would have gotten like a 4.9 or a 4.8 because of the late penalty. What's your name? Riley. All right. Before I get talking about today's topic, does anyone have any questions on the exam? Feel free, one second. Feel free to come talk to me, either after class or during my office hours for more understanding about where you may have gone wrong. I often recommend to students to take a few moments to review your exam. I know it's very disheartening to see your scores, but it's a good idea to review your exam to understand, number one, did I make a mistake because I read too quickly, because I misunderstood the instructions? That's something that you can work on for future exams. One of the biggest benefits of my class is you get lecture and lab to do the exam, 4 hours and 20 minutes. So I hope that rushing should not really be an issue. Number two, if you review the exam, you might recognize, oh, this was just a fundamental misunderstanding of the topic. That's something that you can come to me and we can talk about, and I can help you better understand that. Joel, I saw your hand, but I saw Alina's hand first. What's up? Yep. Let's see if I can find it on our notes. Right here in orange, transition metals lose from s orbital first. And I actually gave the exact example on the exam, Fe2+. I do that a lot. I use questions and examples from my notes and put them on exams. Joel, what was your question? That's the same question. Yeah, we just lose from the s orbital first. So that was a good one. Did I answer that though? Any other questions based off that, or are you good? So I'll go back to where it is on the notes. Mm-hmm. Okay, so this is the same for the Fe example. So right here is a really good explanation for that. If you wrote neutral iron, that would be the full configuration 4s2 3d6. It's from the neutral you remove 2 electrons. You always do that first instead of just trying to make the more stable one. You start from the neutral and then you remove. Yeah. Any other questions about the exam? Okay. Let's get to work on today's topic. We're actually starting module exam 2 content. This looks a little awkward. One second. Okay. Now, something that regularly comes up is the idea of the cumulative nature of this class. Technically speaking, of course, I will not ask you for material or questions based off of module exam 1. However, some of the details we covered in module exam 1 will come back. I think of most notably naming. Right, we're heading to a part of our section of our syllabus where we'll be talking about reactions and chemical compounds, and we just won't have the time to break down each independent name and how we got them, as well as the formula. So nomenclature would probably be what I would recommend to be the one topic everyone reviews, because of course we'll hit the ground running come next week when it comes about reactions. All right. Starting module exam 2, we're moving on to our latest topic. We're talking about the mole concept. Now, to understand the mole, we should first understand the value of $1. let's think about what a dollar means in our day-to-day language. And I promise you this is going somewhere. A dollar, of course, is one of our basic units of currency. Well, that looks so awkward. And a dollar, at least in USD, represents one of the most fundamentally well understood ideas. You can go to any store, any gas station, any Target or otherwise and say, hey, what does this cost? They tell you a dollar and you know exactly what that means. But in our reality, that $1 can take many other forms. What do I mean by that specifically? I mean, 4 quarters adds up to a dollar. 10 dimes add up to a dollar. 20 nickels add up to a dollar. And 100 pennies add up to a dollar. And we understand all of these things fundamentally. If you ever did laundry at a laundromat or in a college dorm or any just type of situation, probably would have told you like, yeah, it's cost $1.25 to do laundry. That's 5 quarters. If you've ever gone to a convenience store, needed to get a couple pennies, change your cash into coins, or get cash from your coins, you know exactly the type of language we use in our day-to-day. But when we go to the store, we don't say that a bottle of water costs 150 pennies. We don't say that a bottle of water costs 6 quarters. We don't use these language. We just simply say that it's $1.50. It's not that the quarters or the pennies are wrong. It's just that's not really the terminology we use that's well understood. In the same way, I want us to think about the mole as a chemical currency. Where 1 mole can mean many, many, many things. Just like $1 means 4 quarters, 10 dimes, 20 nickels, and 100 pennies. However, we do have situations where that mole can take many different forms. The big rule of thumb is 1 mole is equal to 6.023 times 10 to the 23 of anything. I really want you to keep going back to that $1 analogy where it's the same thing, $1, 4 quarters, 10 dimes. They're just different ways that we can talk about this. But the mole represents the traditional form of currency that we use. This number, 6.023 times 10 to the 23, is not just a random number. It's known as Avogadro's number. And Avogadro's number is incredibly useful because, again, it allows us to quantify 1 mole of anything. What this tells us, for example, is that 1 mole of O2, so 1 mole of oxygen, is equal to 6.023 times 10 to the 23 atoms of oxygen. So now that we have a count, we can able to say that in 1 mole of oxygen, there are that Avogadro's number of atoms. We can also further relate it to mass, where 1 mole of a compound, of a chemical compound, is equal to the atomic mass / molecular mass. Now that word right there, I see your hand, Joel, I'll give you a second. That word right there, molecular or molecular mass, that's not a term that we've regularly used before, but I just want to kind of define the use of atoms versus molecular. If I were talking about something like, I don't know, let's say fluorine, F2, we would use atomic mass. Why? Because it's a single atom, fluorine. Even though there's two of them, it's still just fluorine. So we would use atomic mass and we would describe this as atoms. Take, for example, another molecule, another compound such as H2O. H2O is a combination of two different atoms. And as a result, we refer to it using molecular mass. So the two terms mean the same thing. They're both mass of the compound or the element. It's just a difference of what do you use when referring to an element or more than one element. In the same code of logic for molecular mass, we sometimes use molecules. What does that mean? That means that 1 mole of water, H2O, is equal to 6.023 times 10 to the 23 molecules. Earlier for oxygen, we had said the same thing, but we used the term atoms. I just want to really make it clear that the use of the word atoms or molecules simply depends on if you're working with a molecule of two different atoms or just a single atom. Joel, what was your question? Correct. It stands for or. Thank you for clarifying that. And as we just learned, 1 mole of anything is also its molecular mass. So 1 mole of H2O is equal to the molar mass of hydrogen, of which there are 2, added to the atomic mass of oxygen, of which there are 1. Looking at our periodic table, the atomic mass of hydrogen is approximately 1. The atomic mass of oxygen is approximately 16. This is how we're able to say 1 mole of water is approximately 18 grams. This is what's known as the molar mass. It is the mass of 1 mole. Here's what the big implication is. 1 mole of anything, let me put this in the center actually. 1 mole of anything is equal to Avogadro's number, 6.023 times 10 to the 23. And this can either be atoms or molecules. 1 mole of anything is also equal to the molar mass of that element or compound. And molar mass will traditionally be grams divided by moles, grams over moles. In this case, that line is a division, not an or. And with this very simple idea, where all 3 of these terms are equated, we can recall a general principle from algebra that says in the case of A equal B, which is equal to C, this directly implies that A is also equal to C. If all 3 are equal to one another, we're able to equate 2 of the extremes, 2 on the opposite end. So the big takeaway from this, of course, is recognizing the molar mass of anything is equal to Avogadro's number, 6.023 times 10 to the 23 atoms or molecules. How exactly do we use this in math? How do we use this in our type of questions? Well, fortunately for you, there are actually 2 formulae. N is equal to small m divided by molar mass. Number of moles is equal to Avogadro's number. Sorry, let me, yeah, oops. Is equal to What's the symbol for this one again? I apologize. Capital N divided by capital N sub A. I'll define what each of these terms mean. The lowercase m is number of moles. Lowercase m is the mass of the sample. Uppercase M or mm is the molar mass. On the right equation, N again means number of moles. Na is Avogadro's number. And capital N is number of atoms or molecules. These are the two formulae that I'm now officially introducing that you are expected to memorize and know how to manipulate and use, because this will guide all of our calculations from henceforward. Let's do a couple of practice questions. Everyone should have a copy of the problem set everyone should have a copy of the problem set. Either I handed it out to you or you picked them up at the beginning or front of the class. Yeah. Where is it? Yeah, there it is. Let's do a couple questions from page 2, problem 2. And I'm going to have those formulae at the ready. N is equal to M over MM. N is equal to capital N over N sub A. These are the two formulae that we're going to regularly refer to when dealing with some of these questions. Let's actually start with problem F, one of the simpler ones. All right, the question just states, how much does 1.4 moles of AlPO4 weigh? All right, so what do we know? What do we know we're working with here? We know we have two primary formula. I'm writing them here again, M over MM, and N is equal to N over sub A. The question is ultimately asking what is the mass of that sample? You can see the units are grams. So immediately we know this is what we're trying to solve, that small m. All right. Do we know how many moles are present? Yes, the question does specifically tell us 1.4. So everything so far is telling us this is the equation we must use. The only thing that's missing, of course, is the molar mass. You'll notice that I did not provide this to you as part of the question. However, you are able to calculate the molar mass using your periodic table. Mass is what we're trying to find, and we're told that the number of moles is 1.4. So it's on us to calculate the molar mass of aluminum phosphate. We see that in the molecule, there is one aluminum, there is one phosphorus, and there are 4 oxygens. So we are going to get our periodic tables out, and we are going to calculate the mass of aluminum phosphate. I want everyone to find the periodic table and do the math themselves. You're going to round it to the whole number. Aluminum plus phosphorus plus 4 oxygens. All right, when I find it on the periodic table, aluminum is 27 grams when rounded. Phosphorus is 31. There are 4 oxygens, of which each is around 16 grams. We put this on our calculator, 4 times 16. It's a 31 plus 27. We get 122 grams per mole. Now that we have the molar mass in hand, we can plug it into our equation. N is equal to 1.4. We're trying to find M as in mass, and the molar mass is 122. A little bit of algebra skills tell us that we can cross multiply such that we can say M is equal to 1.4 times 122. Putting this in our calculator, we get 170.8 grams. Now, we're not done just quite yet. Do remember that the overall instructions do say, report your answer to 3 significant figures. We count from left to right, 1, 2, 3. After the third tells us if we should round up or round down. That's an 8. That's what tells us our final answer will be 171 grams. You also could have written this in scientific notation, 1.71 times 10 to the 2 grams. Both would be correct. So we're getting into a point of the curriculum where we're now actively going to start using our calculators. And as pointed out from the module exam, for some of us, using our calculators still represents an issue. Don't worry, though, you'll get a lot of practice over this next module, especially with these kinds of questions. I'd like to try another one. Let's see. I would like to do part C, or letter C. All right. Getting our formulae at the ready so we know which one to use. N is equal to mass over molar mass. N is equal to number of atoms or molecules over Avogadro's number. Let's look at what the question's asking us. Ultimately, the question is asking us for gram. It's asking us for mass. So we know we need to have M in there somewhere. However, it's given us the number of molecules. That's N. As you can see, there is no single equation that relates M and N. So what do we need to do? We need to put them together. Remember, by that rule of A equal B equals C, we're able to say A is equal to C. We can say that since N is equal to the same thing, N over N sub A and M over MM, we can come up with a new formula that says M over MM is equal to N over N sub A. Remember that this ultimately comes back to the idea that if A is equal to B and B is equal to C, we can say that A is equal to C. Now that we have the formula in hand, we can take a second to identify what we need to know and what we don't know. Just make this a little bit smaller so it's out of our way. Ultimately, we're trying to find the mass. That's what the question's asking for. We know the number of particles, the number of molecules is 1.03 times 10 to the 23. We know Avogadro's number, that's a constant, that's 6.023 times 10 to the 23. Check, check. That's what we're trying to find. All that's left, of course, is the molar mass. We can calculate that ourselves. The molar mass is equal to the sum of masses. We have 2 hydrogens and 2 oxygens. 2 times 1 added to 2 times 16. That's going to be equal to approximately 34 grams per mole. You have a choice depending on your comfort with math. You can immediately plug in the values and then manipulate, or you can manipulate the equation first and then plug in. Doesn't matter which is to me because it just depends on your comfort level with math. I'm going to manipulate first. We want to get M alone. So we have to get MM over onto the other side. How do we do that? We multiply both sides by MM. By multiplying both sides by MM, we can cancel out the denominator on the left such that what we're left with is M is equal to MM multiplied by N over N sub A. All I've done is multiply MM on both sides. Since I have all my values at the ready, I can just plug them in. 34 times 1.03 times 10 to the 23 all over 6.023 times 10 to the 23. This is where your calculators will really, really come in handy. Don't like this new update because it is anyway. All right, so we have 34 times, and we have a math fraction. On top, we have 1.03 times 10 raised to the 23 all over 6.023 times 10 raised to the 23. Plugging this into our calculator, we get 5.814. That's a big, long number. I'll just write the first 3 decimal places. This is equal to 5.814. This is grams because we know we're calculating mass. The question specifically said to round to 3 significant figures from left to right, 1, 2, 3. After the third tells us if we should round up or round down. That's a 4. So we just erase it such that our final answer is 5.81. So math skills will really, really come into play in this section. If you find yourself struggling with the math, with the formula manipulation, please come talk to me. We can schedule office hours. We can set up an appointment to go over that basic algebra. Yeah, what's your question? Because the formula is H2O2. Yes, because I'm saying there are 2 hydrogens and there are 2 oxygens. So when I plug in my masses, it's just better for me, easier for me to see what I'm reading. Any other questions on either one of these 2 questions? Yes, Naomi. Yes, so the fraction over here tells us we'll be doing 34 times this entire fraction, which is exactly what I put into my calculator. Is that what you're asking? So you will eventually need to plug in. Let me just show you what I mean by depending on your comfort level. So starting again with that, M over MM is equal to N over N sub A. Obviously, what I did on this page was I manipulated the formula first, then plugged in. Some people can plug in immediately to say M over 34 is equal to 1.03? Yeah, 1.03 times 10 to the 23 all over 6.023 times 10 to the 23. You would still arrive at the same conclusion. You'd multiply both sides by 34, and that would still lead you to the same idea that mass is equal to 34 times that entire fraction. It just depends on your comfort level with math. When numbers start to be included, a lot of people's brains go on the fritz. So it's a lot easier to manipulate letters than it is to manipulate numbers. But you should still get the same answer overall. It's just a matter of which one you do first. Do we plug in and then manipulate, or manipulate then plug in? Okay. That takes care of what the mole is. It is our chemical currency that allows us to measure different scales and quantities of atoms or molecules, while also giving us an idea into, well, quite literally, how much of something there is. Another tool that becomes very useful in our discussion is a concept of percent composition. It's easier to explain to you what percent composition is by use of a question. So I'll simply write, the question is, what is the percent composition of each element in the molecule C2H5OH? The formula to determine percent composition, percentage comp, is equal to the mass of the elements divided by the molar mass of the compound times 100. So the first one we're going to do is the percentage of carbon present. Obviously, in all of these cases, we will eventually need the molar mass of the compound. So let's just take a second to identify that. The molar mass is going to be equal to, let's see how many atoms there are. We have 2 carbons, we have 6 hydrogens, and we have 1 oxygen. Recognize where those numbers are coming from. C2 tells us we have 2 carbons. We have an H5 and another H, so 6 hydrogens in total. And we have that single oxygen right there. We have 2 times 12, 6 times 1 plus 16. 24 plus 6 is 30. 30 plus 16 is 46 grams per mole. So we have the molar mass. What we need now, of course, is the mass of the elements. All right. In the compound, there are 2 carbons. Each carbon is 12 grams, and there are 2 of them. So the total mass of the element is 24. That'll be divided by the molar mass, 46, times 100. Putting this into our calculator, 24 divided by 46 times 100 is equal to approximately 52%. Would like everyone to now try to calculate the percent of hydrogen present as well as the percent of oxygen present. Take around 4 minutes to do that. Yes, problem. So there are 2 carbons. Each of them is 12 grams. 2 times 12 is 24. So for the mass of the hydrogen, there are in total 6 hydrogens. So the mass would be 6. For the oxygen, there is only 1 oxygen. So the mass of the oxygen in the compound would be 16. Some people Karen. Kathleen. Yep. Miguel. Okay. Oh, yes. For percentages, yes, we don't traditionally use decimals for percentages. Yeah. Definitely. 35. Yeah. Okay. Hopefully that should be enough time. So starting with the hydrogen, there are in total 6 hydrogens present. Each hydrogen is 1 gram, so that's 6 in total. The molar mass is 46, so 6 over 46 times 100. 6 divided by 46 times 100 is approximately 13%. A student asked, and I pointed out that for percentages, we traditionally just round to the whole number. Same thing for the molar mass. So it's convention to round to the whole number. Oxygen, the same idea. There is 1 oxygen. Its mass is 16. Molar mass is 46 times 100. This right here is approximately 35%. So percent composition is a fairly straightforward concept. It's just the amount of an element present in a molecule. Percent composition, or understanding what percent composition is, leads us directly into our next big topic. Empirical and molecular formulae. All right, let's do a little definitions. The empirical formulae of a molecule, or EF for short, formula, is the simplest whole number ratio of atoms. Of atoms in a molecule. The molecular formula, MF, is the exact whole number ratio. What does this mean and what does it look like? Well, if I were to compare a variety of molecular formulas and empirical formulas shown here, an example of a molecular formula is C6H12O6. Our biology majors may recognize this. Not relevant to the class of this class, of course, but C6H12O6 is actually glucose. We see here that this molecule consists of carbons, hydrogens, and oxygens. We see that for every 6 carbons, there are 12 hydrogens, there are 6 oxygens. It should be perfectly clear that this is not the lowest whole number ratio. In fact, we can simplify this even further to CH2O. That basically says the same thing. For every 1 carbon, there are 2 hydrogens. And for every 1 carbon, there is 1 oxygen. We can take another molecule, such as C3H6O3, which is another sugar, and we can further get an empirical formula from this. The same idea, we just reduce it. This becomes CH2O. And this brings up a very important aspect of empirical formula. A lot of compounds will have the same empirical formula. Over here on the right, the molecular formula, the exact whole number ratio. These are 2 completely different sugars. They serve different purposes, they look different, they're used differently. But their empirical formula, CH2O, are the same. The overall implication of this is that if their empirical formula is the same, then we predict them to be similar properties and characteristics. Meaning, if I ever see a new molecule, if a new molecule were ever invented, let's say C100H200O100, a brand new molecule of almost 400 atoms, I may not know what this molecule is right off the bat, but I can get the empirical formula to CH2 and I can say to myself, you know what? If I were to take a lucky guess, I would probably say that this is some sort of sugar. I don't know what type of sugar, I don't know where it would be used, but I can at least take an educated guess to say, since this matches other sugars, chances are it shares similar properties. There are going to be some cases where the molecular formula, such as H2O, is as simple as it can get. You cannot reduce this anymore. In these cases, the molecular formula is the empirical formula. But it's important to understand that this is just different ways of telling us the same thing. Empirical formula is the lowest whole number ratio. When multiple structures have similar empirical formulae, they are predicted to have similar characteristics. And in some cases, the molecular formula and the empirical formula are one and the same. So what do we do with this? How do we use this? And how do we calculate it? Let's do a question. The one that I've written, I don't know if this is on the problem set, so let's actually do this one. How to calculate empirical formula Here's the question. What is the empirical formula, here written as this EF, of a molecule that consists of 78.14% carbon, 12.86% oxygen, and 9% hydrogen? We know what these percentages mean. They're the percent composition. We know where they come from. We know how to calculate them. Now we're just using them to determine the empirical formula. The approach is very consistent. It's very tabular, though. We're going to draw a table. It'll have 4 columns in total. The first column is unnamed, and the other columns are the atoms in question. It does not matter the order in which you write the columns. I just wrote them in the order the question is, well, I didn't even write them in the order the question gave us. I just wrote them in whatever order I wanted. The order does not matter. The very first thing we're going to write is the percentages. Okay, well, this is actually straight from the question. So that's just writing down numbers. The carbon is 78.14. Actually, let me try to use the same colors for consistency. 78.14% for carbon. 9.0 for hydrogen. Whoops, use the wrong color. 9.0 for hydrogen and 12.86 for oxygen. The next thing we're going to do is we are going to assume the total mass is 100 grams. This is an assumption that we make because if we add up all of the percentages, 78.4 added to 12.86 added to 9, you would get 100%. So by assuming the total mass is 100 grams, we're able to say that, well, 9% of 100 is just 9. So by making this assumption, we can calculate these assumed masses. The mass of the carbon is 78.14. The mass of the hydrogen is 9.0. And the mass of the oxygen is 12.86. So yes, you are writing the exact same numbers, but recognize that the first one is a percentage, and then we assume a mass based off of that percentage. Once we get the assumed mass, we will then calculate the number of moles of each element. And if you recall, I'll write it over here. The number of moles of anything is equal to the mass divided by the molar mass. In the case of carbon, the mass is 78.14. From our periodic table, the molar mass of carbon is 12. The mass of hydrogen is 9. From our periodic table, we know the molar mass of hydrogen is 1. The mass of the oxygen is 12.86. We know that the molar mass is 16. If we put all of this into our calculator, we get for carbon 6.5. For hydrogen, 9. And for oxygen, 0.80. After this, we will then divide all numbers above by the lowest number, which you should be able to identify as the 0.8. Of the three numbers, we're going to divide all of them by the lowest number, which we quickly identify as 0.8. This is what gives us the ratio such that we have 6.5 divided by 0.8. 9 divided by 0.8, and of course, 0.8 divided by 0.8. We're dividing all of the number of moles by the lowest number. We put these into our calculator. In the case of carbon, we get 8.13. In the case of hydrogen, we get 11.3. And in the case of oxygen, to no one's surprise, this is just a flat 1. Anything divided by itself is just 1. Now that we have the ratio, we are now able to say that for the molecule, we have 8 carbons for every 11 hydrogens for every 1 oxygen. And this right here is the empirical formula of the molecule in question. This is a procedure that you are expected to follow. While you don't necessarily always need to draw the table, the order is here. From the percentages, we will assume mass. From the assumed mass, we will calculate moles. From the moles, we will divide to get ratio. And that's what gives us our empirical formula. I'm going to do another question of this type, but before I do that, does anyone have any questions before I move on? All right. Same type of question, but just a different set of numbers and molecules. The question says a gasoline additive consists of the following: 72% chlorine, 23% carbon, and 5% hydrogen. The question being asked is, what is its empirical formula? And the second part of the question says, if the molar mass of the additive is known to be 100 grams per mole, what is its molecular formula? So this question is actually asking for two things. We're asking you for number one, what is the empirical formula? And number two, what is the molecular formula? So two answers. Let's do the empirical formula first, so part A. We're going to draw that table again. We know we have 3 elements, so we're going to have four columns, sorry. Cl, carbon, and hydrogen. The very first thing we know is from the question, the percentages, 72, 23, and 5. That's straight from the question. From there, we're going to assume the mass, assuming that the total mass is 100, it's just the exact same set of numbers, 72, 23, and 5. From the assumed mass, we can then calculate the number of moles. 72 divided by the atomic mass of chlorine, that's 35.5. For carbon, 23 divided by its atomic mass, that's 12. And in the case of hydrogen, that's 5 divided by 1. If we put these into our calculator, in the case of chlorine, 72 divided by 35.5 is 2.02. (23 divided by 12 is approximately 1.92. 5 divided by 1 is just plain 5. Now we're going to get the ratio, which we get by dividing all of those numbers by the lowest. The one you should recognize as the lowest is 1.92. So we have 2.02 divided by 1.92, 1.92 divided by 1.92, and then 5 divided by 1.92. In the first case for chlorine, 2.02 divided by 1.92 is approximately 1.05. Any number divided by itself is just a flat 1. And then finally, 5 divided by 1.92 is 2.6. Now that we have the ratio, we can say that the empirical formula, there is 1 chlorine. Remember, the ratio was 1.05. That's rounded to 1. There is 1 carbon. And for the hydrogen, there are 2, not 3. I did not round up for 2.6. The reason is when dealing with empirical formulae, you only round up if the ratio is greater than or equal to 0.9. The reason for that is more logistical. It's safer to round down to 2 than to round up to 3, because if you're wrong, you're basically saying you're making up 0.4 amount of that atom. And it's just like, where is this coming from? Are you just making up matter? But we can confidently say that there is at least 2. So the rule for rounding up when dealing with empirical formulae is that you only round up if the ratio is over 0.9. So if this were 2.9, it would round up to 3. If it were 2.88, it would round to 2. So it is on me as the instructor, the one making the questions, to make sure that it's not ambiguous at all. We're not done yet. We have gotten the empirical formula. That's right there. The next part, part B, says, if the molar mass of the additive is known to be 100 grams per mole, what is its molecular formula? Well, fortunately for you, there's an explicit formula to do this. MF is equal to the molar mass of the sample divided by the molar mass of the empirical formula multiplied by the empirical formula. We know from the question the molar mass of the sample, that's 100 grams. That was in the question. It did say the molar mass is known to be 100 grams. What we need, of course, is the molar mass of the empirical formula. So let's take a second to calculate that. There is 1 chlorine, 1 carbon, and 2 hydrogens. This is equal to 35.5 added to 12 added to 2. This is equal to 49.5 grams. The molar mass of the sample is 100. The molar mass of the empirical formula is 49.5. And the empirical formula itself is ClCH2. (100) divided by 49.5, when rounded, is approximately 2. So 2 times ClCH2, that's how much we need. We know in total this means there will be 2 chlorines, 2 carbons, and 4 hydrogens. The empirical formula is the lowest whole number ratio. The molecular formula is the exact ratio. That was a lot of content covered in the last 1 hour. I know we got a late start because of the exam review, but let's just get the extra credit out of the way. For problem 2, the extra credit is any 10 questions. The extra credit for problem 2 is any 10 questions. The extra credit for problem 3 is the entirety of page 3. So I'll repeat myself. The extra credit was problem 2, any 10 questions, and all of page 3, problem 3. Everything else is for your own practice slash studying. Of course, do let me know if you have any issues. You can come talk to me in office hours or set up a meeting. This is a very math heavy section, so I do understand if you need additional help. Please come talk to me. It is 1:16. We're going to end lecture for here for today. We have lab in about 15 minutes in room 604. I'll see you guys then.